graphing radical functions. Recently, we just graphed rationals. So instead of rewriting everything in for you like I'm going to do in class today, I have it filled out already. And I'm going to kind of highlight some stuff. So general form, we have, well, let's look at parent function first. We have y equals the square root of x. So that would be our parent function. And so then when we look at the general form, y equals a times the square root of x minus h plus k. And so just like before, with all these other functions, a is our leading coefficient, h is the opposite sign of the inside value, and k is the ending constant. It's the single number that's not inside the square root symbol. So let's look at a little closer. If a is positive, that means the graph is opening up and it has a minimum. So you can look and see the shape of the graph below. It's a dot, a point, and then it goes up and towards the right. If a is negative, it opens down and has a max. Very similar to our quadratics, that went at positive and negative. But now it just has a single point to the left and it goes down and to the right. If a is between 0 and 1, then we say the graph is compressed. And if a is greater than 1, we say it is stretched. Now, h and k, if you remember in rationals, we said that was the intersection of asymptotes. Other times it's been our vertex. For radicals, it is our endpoint. So if you look back over here, our endpoint were those 2 points there. So endpoint hk. And so now the h value identifies the horizontal shift, so that's left and right. And the k value tells you the maximum and value and also the up and down shift. Remember, x's lie to you, so the h value, it's always opposite. If it's plus, it goes to the left, and if it's minus, it goes to the right, just like we did with rationals and quadratics and everything else. The k value, if it's positive, goes up, and if it's negative, goes down. So let's look at a couple simple examples. And so you can see I've drawn, if we look at to the left, I've drawn the parent function in over there where it hits at 0.00, 1, 1, and 4, 2. Now when we have y is 2 times the square root of x, that means when we plug in 1 for x, y is now 2 times the square root of 1. When we plug in 4 for x, y is now 4 as well. And so when we're dealing with square roots, we always want to deal with x values that are perfect squares. So that would be like 1, 4, 9, like you see here. So those are the first 3 perfect squares. And then you can see over here when we have 1/2 of the square root of x where it's compressed, you can see how the graph is now closer to the x-axis. And so now when we have shifts, so square root of x minus 3 with the minus 3 inside, that means now we're shifting 3 to the right. So our parent function is here, and now each point gets moved 3 to the right. And so that's, you can shift from 0, 0 to 3, 0, from 1, 1 to 4, 1, from 4, 2 to 7, 2. And then the last one, square root of x minus 3, means we shifted 3 down. So you can see how the comparison between the parent function and the actual function are. Each point is moved down 3. All right, so let's flip it over to the other side. And I have 7 examples here. So let's look at these. And I'm going to edit. I'm going to stop highlighting and I'm going to write in red, I think. Let's see what options it gives me. So I'm writing it pretty big. Okay. So says graph the equation, name the endpoint, and describe the transformations. So you can see if I was going to graph the parent function, which probably for each one I'm at 0, 0, 1, 1, 4, 2, and 9, 3, not 9, 4, 9, 3. And so that's my parent function right there. And so you can see 1/3 times the square root of x means it's going to be compressed by 1/3. The endpoint is still 0, 0 because it didn't shift left to right or up or down. If we look at the number 2, y equals -2 times the square root of x minus 2. So I'm going to draw the parent function in again, 0, 0, 1, 1, 4, 2, 9, 3. I'm going to connect those points. And so now you can see the -2, we're going to back to saying reflect across the x-axis for the negative sign. For the 2 out front, we'd say stretched by 2. And then the -2 in the back means it's shift down 2. So you can see we shifted down 2, we flipped it upside down, and then we stretched it by 2. And so I still I made a little chart or table for myself. So I know from 0, 0, the endpoint, I'm moving down 2. So I did that. That's that right there. Right there. But then I looked, when I plugged in 1 for x, that's -2 times 1 minus 2. When I plugged in 4 for x, that's -2 times the square root of 4, which is 2, minus 2. So you can see how I found my points. And then we have number 3. I'm going to draw in the parent function again. 0, 0, 1, 1, 4, 2, 9, 3. What would be the next point? Right, 16, 4. So you can see the graph gets flatter and flatter as we go. So this, you can see, it reflects and it moves down 1. And so it's interesting how close this graph, you can see how it reflects, because it basically, if you had a mirror right down the middle here, you could almost flip them on top of each other if we hadn't had that shift down 1. So that's why the endpoint is at 1, 0, -1. And then you can see I plugged in my x values for 1, 4, and 9 to see what would happen. All right, so now let's look at 4. At number 4, I'm going to plug in my parent function 0, 0, 1, 1, 4, 2, 9, 3, and draw it in. So we have 2 times the square root of x minus 3 minus 3. So you can see I say we stretched by 2, shifted to the right 3, and shifted down 3. So that's how we got our endpoint at 3, -3 right here. Now, with our other points, we have to plug in values. So I would plug in, my next value for x I would choose would be 4, because that's 1 to the right. So 4 minus 3 I know is 1. I know what the square root of 1 is. That's 1. So it's 2 times 1 minus 3. That puts me at 4, -1. Then I chose 7 as the next point after that, because I know what 7 minus 3 is. That's 4. The square root of 4 is 2. 2 times 2, 4 minus 3, which is 1. And that's the last one that fits inside the graph we have. So hopefully that makes sense. I'm going to draw the parent function for number 5. We have 0, 0, 1, 1, 4, 2, and 9, 3. We have square root of x plus 2 inside the square root sign minus 2. So that means we shifted left 2 and down 2. And our endpoint is at -2, -2 over here. And so you can kind of see I already wrote in the numbers I'm going to use for x. I'm going to use -1, 2, and 7, because -1 plus 2 gives me 1, 2 plus 2 gives me 4, and 7 plus 2 gives me 9. Those are all the perfect squares, 1, 4, and 9. And so then it's just 1 minus 2, 2 minus 2, and 3. minus 2. So you can kind of see how I got those points. And the last one, once again, I'm going to enter in my parent function at 0, 0, 1, 1, 4, 2, and 9, 3. And you can see x minus 3 and then the plus 1, right 3, up 1. My endpoint is at 3, 1. And so the points I would pick here, I would pick 4 and I'd pick 7. And you can see that's what I did. Got a point here and a point here. The next point I would have picked would have been 12, but 12 is off the board. So that's why. All right, and then this last, oh, I forgot there's 8. The last 2. So write a square root function matching the description. The parent function is f of x equals square root of x is translated down 2 units and 6 units left. So down 2 on the outside and 6 units left on the inside. Left plus 6. All right, write the function shown in the graph. So if you look at number 8, we found our endpoint is at 0, negative 3. So that means our h value is 0 and our k value is negative 3. So that's how we got that and that there. How did we get 2? Well, we know normally when we move 1 to the right, we only move 1 up. That would put us right here. But if we look, we moved up 2. So we have to think, what number multiplied by 1 gives us 2? Well, 2. So that's why our a value is 2. So there we go. F of x equals 2 times the square root of x minus 3. So hopefully that has helped you with graphing radical functions. Be sure to follow my YouTube. This has been Coach Melling.